Okay, so the test you'll be taking, is timed for 45 minutes, just so we can fit it comfortably into the lecture slot. Okay, so we can get everybody in and sat down and started and out the door again at the end. So it's timed for 45 minutes. There's actually going to be 12 questions on your test. So like this mock test 2, 6 questions on my half, 6 questions on Saeed's half. Mock test 1 is 14 questions on it, I think. Okay, so let's talk through some of these. Let me zoom in a bit here. Okay, so this first one, they kind of get progressively harder as you go from the first question on to the end. So mock test 2, question 1. So this is a quite straightforward question to get you started. I would hope everybody, without exception, would obtain full marks on this. Okay, so we've got a sequence here defined by this expression, and it's a sequence going from n equals 1 to infinity, so a1, a2, a3, and so on. And the question simply asks, what's the value of a4? So it's just a matter of substituting n equals 4 into the formula. Not too hard, okay? So we substitute n equals 4 into this to obtain a4. And you're given 4 options there of fractions, so we just have to work out which one it is. So a4 here should be 2 times 7 squared over 4 factorial. So just need to evaluate that. So it's 2 times 49. 2 times 49 over 4 by 3 by 2 by 1. We'll see if we can simplify it any. We can cancel those 2's. There's no other cancelling that we can do, I don't think. 49 is 7 times 7. So, unless I made a mistake, this should be 49 over 12. So that is indeed one of the options there. It's option A. 49 over 12. Okay. I guess just things to be aware of there is, you might also see n in the exponent position in such a formula, and just be careful that you're using the correct definition of factorials and so on. There's really not a whole lot to say, it's just some straightforward algebra. Question 2. Got question 1. So question 2 again gives you a formula for a sequence. So this is sequence Bn. Bn is defined as 2n minus 1 over n plus 1 squared. And here I'm asking you to find the expression for the element Bn plus 2. The n plus 2 element. Now you notice a couple of things there. I've suddenly switched. I'm using an index m now, but that's okay. After all, these are just letters. These are just labels for the subscript index of the sequence letter. So I'm asking for Bn plus 2, so as the options all look reasonable, they're all rational functions in M, quotients of polynomials in M, so we just have to obtain the correct one. Now, again, this is fairly straightforward. It's just a matter of substitution and simplifying the expression algebraically. But every year I do find people making errors in doing this, not doing the substituting correctly. Okay? So let's have a look at what this should be. So question 2. So to find Bn plus 2. Substitute n equal to n plus 2 into the given formula. And the kind of place where people do go wrong is they'll see a 2n minus 1. So they think, well, if you evaluate that at n plus 2, it's going to be 2n minus 2, or something, 2n plus 2. They don't fully appreciate that you have to substitute n plus 2 into the place where n was before. So 2 is multiplying the index n. So if our new index is n plus 2, then 2 has to multiply all of n plus 2, and you subtract it. And then at the bottom, we've got n plus 1 all squared. So 1 greater than the index squared. So that, for us here, is going to be n plus 3 all squared. And that isn't one of the options, because see, there's maybe a bit of tidying up to do. So when you multiply out the numerator, of course, you see 2m plus 3. And you can square out the denominator, and that will give you m squared 6m plus 9. And is that one of those? Yeah, it's option C. Okay. Is that okay? Any queries? Queries on that type of question? Do be careful with these kind of questions. Do check and double check them, because some of the other options I've given there are ones that match kind of common mistakes that people might make. I'm not going to write down the common mistake, because I don't want you to take it down and then think that it's true or that. But you know, here, look, I've placed all of n plus 2 inside this bracket here, because 2 times the index minus 1. Here I have n plus 2, so n plus 2 is the new index. Places where people might go wrong is they might just write down 2m plus 2. So not multiplying this 2 here by the coefficient 2. You might just simply multiply the n by the 2 and then leave this 2 unmultiplied. A common kind of mistake that people might make. Is that okay? Anything more to say on that? Changed it this week, 9:15. Okay, let's go to question 3. Everybody got that? Okay, so the questions are getting slightly more sophisticated. So here we're talking about convergent sequences. So I present you with 2 sequences, a Cn and a Dn, sequence C and a sequence D. The Cn, I'm telling you, is converging to 8/3, and the Dn converges to 10/3. And then the question is about this new sequence, which is manufactured out of the sequences C and D. This new sequence is the sequence Cn divided by 8Dn. Now the question is, so you have to complete this sentence. So this new sequence is convergent with limit 1/80, divergent, convergent with limit 1/24, convergent with limit 1/10. There are a few options. So this is a question. So you solve this using the algebra of limits theorem. The algebra of limits theorem for sequences, okay? So the limit as n goes to infinity of Cn over 8Dn. Well, since both of them are convergent and have limits, okay, and both of these limits are non-zero, we can use the quotient form of the algebra of limits theorem to say that this limit is the quotient of the limits. So the limit of the quotient is the limit at the top divided by the limit at the bottom, And another application of the linearity result says that you can take that factor of 8 outside. The limit of 8 times dn will be 8 times the limit of dn. And now it's a straightforward substitution. As you were told in the question, that the limit of Cn was 8/3, and the limit of dn was 10/3, and that gets multiplied by an 8 as well. So the 8's cancel, the thirds cancel. There's a third above the line, a third below the line. So the only thing you're left with there is 1/10. Is that one of the options? Yeah, option D. So that's the kind of reasoning that leads me to the correct answer there. Any questions about that, or things I could clarify on that? Remember, you can only use this algebra limits theorem to say that the limit of a quotient is the quotient of the limit. You can only say that when the parts of the quotient, the numerator and the denominator, when they have limits themselves. If they don't, then it may need some simplification steps to carry out before. Okay, move on to the next one. So the next one here is question 4. So question 4, and this is a similar type of question. Really it's assessing the same thing, but it's just presented in a different way. It's not sorry, the print isn't coming through very clear there. But this, I'll rewrite out the definition of that. So here we're dealing with the sequence xn, and xn is minus 5n squared minus 2 over 3n squared plus 2n minus 3. Okay, so this is a sequence defined for n equals 1 for all subsequent values of the index n, and we're asking about its limit. So this sequence is converging with limit 0, converging with limit a half, minus a half, minus 5/3, or maybe it's divergent. Okay, so we need to decide the correct answer. So again, this is algebra limits theorem. So the algebra limits theorem is what's needed here after re-expressing the fraction in a suitable way. Because at the moment, xn is expressed as a ratio of sequences, both of which are divergent. Okay, the top sequence is getting larger and larger in the negative direction, without any bound in absolute value, and the denominator is getting larger and larger in the positive direction, without any bound in absolute value. So it doesn't make sense to say the limit of this quotient is the quotient of the limits, because the limits of the top and bottom, they don't exist. However, it is possible to rewrite xn, and we rewrite xn by dividing above and below by the largest power of n that we see in the formula, and that changes xn, or changes the way xn is expressed into minus 5 minus 1 over n, 3 plus 2 over n minus 3 over n squared. And now the algebra of limits theorem can be applied to this. This we can say is the limit of our minus 5 minus 1 over n over the limit of our 3 plus 2 over n minus 3 over n squared. And now both the numerator and the denominator do have limits. And this will be minus 5 over 3. Since all the other parts, the minus 1 over n, 2 over n, the minus 3 over n squared, they all go to 0 as n goes to infinity. So we can use the linearity form of the algebra of limits theorem to take this limit sign inside the bracket and say the limit of this bracket is the linear combination of the limits of the individual sequences. We've got a constant sequence here, so that's limit 3. 2 over n is limit 0, minus 3 over n squared is limit 0. The limit of this combination will be 3 plus 0 minus 0. And a similar reasoning to working out the limit of the numerator. Is that okay? So, which one is that? Minus 5 over 3, that's D again. For that one. So I hope you see that, these questions, as long as you know the material, as long as you know the definitions, and you understand the way that they're applied to certain problems, like we've seen in the tutorial questions, then these questions should be quite straightforward. Remember, our second test, which takes place in the second term, so that's going to be on the second half of this term's material, the material on power series and functions and so on, and on Said's side, predicate logic and so on. That test will be more of a written style question test as opposed to multiple choice questions. And so that one has the potential to be maybe a little bit more challenging. But this initial class test, we've designed it to be relatively straightforward once you have good knowledge of all the material. Okay, then let's go on to the next question. So just a couple more questions to look at. Question 5 here. See that clearly? Yeah. Now, there's a kind of a strong clue or strong hint in this question. It names the type of series that it is. I was feeling quite charitable there, I think, when I wrote this question. If I'm in a more Scroogey mood, I wouldn't include that term, geometric series, there. Perhaps I'd require that you recognize it's a geometric series in order to find the answer. So here we want the sum from n equals 1 to infinity of 7 times 3 over 2 to the n minus 1. Yeah, so the clue is given in the question. So we'll use the geometric series result. This question is a bit too easy, I think, because also the form of the formula exactly matches the pattern. I sometimes make it harder by putting a slight variation in here. Well, what did the geometric series result say? The geometric series result says that this sum from n equals 1 to infinity of AR to the n minus 1 was equal to A over 1 minus R. You do have to be a little bit careful here. If you did it a little bit too unthinkingly, you'd go ahead, you can see you've got your A there and your R. So the A, the initial term, the first term of the series is 7. And the R is 3 over 2. R is the common ratio of terms. But remember, this formula didn't just stand on its own. There was an important condition attached to this formula. What was the condition attached to this formula? Yeah, the absolute value of R has to be less than 1. If the absolute value of R is strictly less than 1, then this summation formula applies. I need to finish the sentence here. As long as absolute value of R is strictly less than 1. Okay. If the absolute value of R is strictly greater than 1, greater than or equal to 1, and A is non-zero, in A being equal to 0 is a very trivial infinite series. It's just 0 plus 0 plus 0 plus 0 plus 0. Okay. Clearly that's convergent, but trivially so. If the absolute value of R is not strictly less than 1, if it's greater than or equal to 1, and you've got a non-zero series, then the series is divergent. So that's the correct conclusion here. So this is divergent, since 3 over 2 strictly greater than 1. Strictly greater than 1, so the terms that you're adding up in this infinite series are growing. Because each time they're 1.5 times the size that they were. The first term is 7, second term is whatever, 10.5. Keep going. Each term in the series is 50% bigger than the previous term. So it's clearly divergent. Remember, when we looked at infinite series, we had our general term test, which said that a necessary condition for any infinite series to converge is that the terms have to be the terms of the series, considered as a sequence, have to be convergent to 0. The necessary condition for convergence. It's not enough for convergence. It's not a sufficient condition for convergence, but it's a necessary one. So here, this series fails that necessary test. Its terms are not decreasing to 0, so it can't converge. So this is divergent since 3 over 2 is greater than 1, which gives it a sequence of increasing terms. So clearly not convergent. The only way an infinite series can converge is if its terms are converging to 0, but even that's not enough. This is our favorite example of a harmonic series, a half plus a third plus a quarter plus a fifth. It has terms which are decreasing to 0, but yet it's still a divergent series. It still grows without any upper bound. So, divergent here, option B. Is that okay? Any related questions there about just the definition of convergence for infinite series and so on? Yeah.
All of the different testing, they're all on the sheet.
They're all, yes.
Okay.
When you look where I posted the 2 mock tests, I've also posted the test handout which you'll have. So yeah, the statements of like the geometric series result, the statements of the general term test, those are all there in the handout. So that's by the general term test. Of course, there's still no harm to learn, to learn them to such a degree that you just know them, then you don't waste time looking through the handout and you've got a good knowledge. In some circles, and especially now we have the internet and everything, everything's accessible to us. Sometimes people talk dismissively about learning things by heart and that. And there's a lot of truth in what they're saying. Some learning by heart is kind of, just see that as the end in itself. Yeah, it's kind of very pointless. But that's not to say that it's not a good skill to have and to develop anyway. If you think in a very different field, like say in the field of music, very creative, it's only in some ways far away from mathematics, very creative, spiritual almost practice. Like some of the greatest musicians in the world, they can play without looking at the music. They know the music off by heart. Now they haven't done that as just a pointless goal in itself, but it's arisen naturally by their kind of intense connection with the music, that they know it off by heart anyway. And you can see similar things in mathematics. If you truly know the general term test, you don't really have a need to look it up. You can, you think of the two as going hand in hand. So don't denigrate learning things by heart too much. I'm not saying that you personally did it, because it's still bad, but that's just broadcast everything. Okay. Right. After that interlude, we come to question 6. Maybe the most trickiest question here. So these multiple choice questions, just because they're multiple choice doesn't mean they're easy by any means. So here, you're given an infinite series. So we're considering the infinite series the sum of Fn, where Fn is given by 1 over the square root of n plus n. Now this already looks quite tricky. This looks kind of borderline. Okay? Remember, the thing to think about with these series like this is to recall the hyperharmonic series. These were the sum from n equals 1 to infinity of 1 over n to the p. This is divergent for all p. Now let me get this right. P is less than or equal to 1. These are divergent series. Of particular note is the case when p equals 1, then we have the harmonic series. And convergent, these were convergent for all p strictly greater than 1. So for each value of p, you've got a different series. And they split nicely into divergent ones and convergent ones. And p equals 1 is the borderline case, but the p equals 1 case is a divergent series, the harmonic series. So this Fn, okay, it isn't hyperharmonic itself. It's a bit more involved because the denominator is the square root of n plus n. So that's not a simple power of n. But you can see it's got an n in there, which is one of the borderline cases, and it's got a square root of n, which is one of the divergent cases. So it is something which is hovering around the borderline, perhaps, between convergence and divergence. So it should be treated very carefully. Now, okay, so what does this question say? Obscure it there. So the question says, only one of the following is a correct application of the standard comparison test to this series. Which one? In the standard comparison test. So we had 2 comparison tests for series, standard comparison test and a limit comparison test. The standard comparison test works by, as its name implies, by comparing the series where, it's a series under question, this series, it compares it to a series that you know the behavior of. Either one you know to be convergent or one you know to be divergent. And if it compares to one of those in the right way, then the series under question has the same behavior as the one it's being compared to. But the comparison goes in two different ways, remember. So let's just revise the standard comparison test before answering this. The reason I've given the hyperharmonic series there is these series, the comparison series you're comparing to, quite often this is one of the hyperharmonic series, or one closely related to one of the hyperharmonic series. So the standard comparison test would say, if you have a known convergent series, and if we can establish this kind of inequality for all n, or at least for every n past some point. So let's say for every n greater than or equal to a for some a greater than or equal to 1. So we don't have to worry about if the comparison isn't strictly met in the first few terms, but as long as the comparison is met after some point, for all terms after that. So this kind of inequality says that the series, the elements of our series behave better than the elements Cn, because our ones are smaller than Cn, or no bigger than Cn. And so if Cn is convergent, then, so this is an if then our series will be convergent also. So that's one half of the comparison test. The other half of the comparison test is where the outcome might be, the conclusion might be divergence. If, on the other hand, you've got a divergent series, and you can make this kind of comparison, that instead now, the terms of the series we're looking at are no smaller than the terms of our divergent series. And this can be done for all n bigger than or equal to a for some a bigger than or equal to 1. So yeah, so we don't have to, sometimes the comparison mightn't work the first few terms. But as long as we can show that it works forever after some point, then this, we interpret this, or you could think of this as saying that the terms of the series we're looking at, they behave worse than the series, than the terms dn. The dn's are behaving bad enough to make the series, sum of dn, diverge, but these are behaving even worse, then the sum of fn will diverge also. So it's a little bit tricky because, so if you compare to a convergent series, you are also convergent. If you compare to a divergent series, you are also divergent. But the comparison works differently depending on what you're comparing yourself to. So, and you can see there in the options given, well, you can't see. See there in the 4 options given, they all look like, just glancing at them, they all look like possible statements that a comparison test might make. Because we all say f of n compares in some way to another term, and then it makes a conclusion about the convergence or divergence of fn. But, which one is going to be the right one. Well, let's come back and look at our Rfn and see what we can do with it. So Rfn equal to 1 over the square root of n plus n. Well, what we can say about this is that this is less than or equal to 1 over n plus n. No, not less than or equal to, greater than or equal to. What have I done? I've replaced one part of the denominator. I've replaced one part of the denominator with something bigger. But when you stick something bigger into the denominator, you make the whole fraction smaller. I mean, really, this is really a strictly less than. It's only less. We only need the equals because of the case n equals 1. Really, in spirit, this should be strictly less than. This is greater than. But if I wanted to apply for all n greater than 1, I need to keep it as the weak inequality. And so this is 1 over 2n. Well, 1 over 2n, the sum of 1 over 2n, which is equal to a half times the sum of 1 over n, this is divergent, since it's the harmonic series. You can say multiple of the harmonic series. The harmonic series is divergent. It grows without any upper bound, so a half of it will also grow without any upper bound. Half as slowly, but still going to get bigger without any upper bound. So we've done the correct comparison with the terms of a divergent series. So therefore, the conclusion should be that F is divergent also. So by the comparison test, our series that we're looking at is divergent also. So that was one of the options. It was option D. I'm interested if you want to go back when you're looking at this. The actual test on Moodle, that was option D. Is that okay? Any questions about that or related questions about the comparison test? There's also the limit comparison test, which we have as well. Okay then, I'll be seeing you again tomorrow afternoon. In the meantime, if there's any particular questions, tutorial questions, mock test questions, or any particular topic you'd really like me to say something about, drop me a quick email today. I'll do my best to include that tomorrow. We also might look at proving one of our results about continuity tomorrow as well. Okay, I'll see you then.